Good morning everyone. Today I'm going to explain you the topic the specific heat capacity from the chapter the thermal property of matter. Before I should explain you the concept, I'm going to pin out the question which is given in the textbook. What are the factors on which the quantity of heat required to raise the temperature of substances depend? Let me repeat the question once again. What are the factors on which the quantity of heat required to raise the temperature of substances depends? In order to answer these questions, I'm going to explain you the small activity which is given in the textbook. In first step, I'm going to take 40 milliliters of water in a beaker and heat it under the temperature by 20 degrees Celsius, and at the same time I'm going to note its time taken. Suppose it takes 5 minutes, and again in the second step I'm going to take a same amount of 40 milliliters of water uh, in a beaker and heat it under the 40 degree uh, temperature using the same source of heat. Here I find it takes about twice the time, and therefore I conclude that the quantity of heat required reaching the twice of temperature by same amount of water. And next, in the third step, uh, I should take a double amount of water. I should say 80 milliliters in a beaker and heat it under the same amount of temperature which I take in the first step, which is 20 degrees Celsius. And here also I found that it takes about twice in order to heat it. And I found that the time taken is again the twice required in the first step. I should say it takes 10 minutes. Then in a final step, instead of taking an water, I'm going to take and 40 milliliters of oils in a beaker and boil it or heat it under the temperature by 20 degrees Celsius. There I come to know that it take a shorter time, therefore the quantity of heat required would be less than that required by the same amount of waters or for the same rise in the temperature. So from the above observations shows that the quantity of a heat required to warm a given substance depends on first its mass m, then second the change in temperature delta T, and the third one's the nature of substances. So the change in the temperature of a substance when a given quantity of a heat is absorbed or rejected by it is characterized by the quantity called the heat capacity of a substance. In mathematically, we can define the heat capacity. The capital letter S of a substance is, or the heat capacity S capital letter is equal to delta Q upon delta T, where delta Q is an amount of heat supplied to that of substances to change its temperature from T to T plus delta T. Also through the activity which I explained in the beginning, you have observed that if a equal amount of heat is added to the equal mass of a different substances, then the resulting temperature change will not be the same. It implies that every substance in a universe has a unique value of the amount of heat absorbed or given off to change the temperature of a unit mass of it by unit 1 unit. This quantity is refers to as an specific heat capacity of a substances. In another word, I should say the specific heat capacity is defined as the amount of heat per unit mass absorbed or given off by the substances to change its temperature by 1 unit. If we take a delta Q stands for the amount of the heat absorbed or given off by the substances of a mass m when it undergoes a temperature change delta T, then the specific heat capacity of that substance is given as small letter s, which is which denotes the specific heat capacity is equal to capital letter S upon m. Since we already know that the capital letter S denotes the heat capacity, which is equal to delta Q upon delta T, so instead of the capital letter S, I'm going to replace it by delta Q upon delta T. So taking m 1 upon n into delta Q upon delta T. So we get the equation of specific heat equal to 1 upon m into delta Q upon delta T. So the specific heat capacity depends on the nature of substances as well as its temperature, and the SI unit of specific heat capacity is joule per kg per Kelvin. Then if normally the amount of substances is given in the mass in the kg, but in some cases the amount of substances is specifically in the terms of moles. Then we can define the heat capacity per mole of a substances by capital letter C is equal to S, which is the specific heat capacity, upon mu, which is mu, and mu instead of, we already know that the S, the capital letter S is the this one, capital letter is S is equal to the heat capacity. So instead of the capital letter S, we are going to take a delta Q upon delta T. So taking a delta Q upon delta T, we get equation 1 upon mu into delta Q upon delta T. Mu is a moles, which is given in the moles. So the C is known as the molar specific heat capacity of a substances. Like the the heat capacity of substances, C also depends on its nature of substances and its temperature. Um, uh, C also depends on the nature of substances and its temperature. Since we take the amount of substances in the mole instead of mass, the SI unit of molar specific heat capacity, capital C, is joule per moles per Kelvins. However, in connection with the specific heat capacity of a gases, additional condition may be needed to define the C, which is molar specific heat capacity. In case the heat transport can be achieved by keeping either the pressure or volume constants. Therefore, the molar specific heat of a gas can be further divided into two, which is molar specific heat capacity at a constant pressure. When we are keeping the pressure constants, then it is molar specific heat capacity at a constant pressure. It is also, in other words, it is also defined as the amount of heat energy required to raise the temperature of 1 moles of a substance by 1 unit at a constant pressure. It is denoted by Cp. And in another way, the taking the volume constants, then it is the molar specific heat capacity at the constant volume. In other words, I can define it as the amount of heat energy required to raise the temperature of 1 mole of substances by 1 unit at a constant volume, and it is denoted by CV. And there is also a relation between Cp and Cv, which is Cp minus Cv equal to R, where R is an universal gas constant, which is 8.314 joule per Kelvin per mole. Thank you everyone.